Welcome. This is Lecture 1 of Informatics 1B, and the lecture title is Getting Started. My name is Perdita Stevens, and I'm going to use here a set of slides which have actually rather a long history. Some of the people who've been associated with previous versions of these slides are Ewan Klein, I think he wrote most of them, Volker Sieker last year, and I've done some editing this year, and as it happened I did some editing quite a few years ago as well. That's often how it goes. Let's set some context for this course. Almost all of you did last semester the course Informatics 1A, in which you were introduced to the basics of functional programming using the programming language Haskell. This semester we're going to introduce you to a different paradigm of programming. We're going to introduce you to imperative object-oriented programming in Java. Now, for many of you, imperative object-oriented programming will be much more familiar. I expect quite a few of you have in fact done some programming in Java before, and if not, perhaps in some other imperative language such as Python. However, we will start at the very beginning. In any case, we are not assuming that you've done any programming before. Let's say a bit about what we mean by imperative object-oriented programming. Well, the classic example of an imperative program is a recipe. Here's a pancake recipe. And the point about this being imperative is that the recipe comprises a number of statements, a number of steps, and they're processed one at a time. First of all, we take a bowl, then we add some flour, then we add some eggs, then we add some milk. Now we've got a slightly more interesting step next. In this stage, instead of saying something like whisk the batter for 5 minutes, which would have been a simple step, we've got a conditional in here. So perhaps we want to say, actually we're not sure how long it's going to take for the batter to become smooth. Depends how hard somebody whisks. So we're going to use a while loop here with a conditional. So the idea here is that we say we expect the reader to check repeatedly whether their batter is smooth yet or not, and if it's not smooth, whisk it some more. And so we've got a loop here. We don't know how long that loop is going to go on, but eventually it will terminate at the point where the batter is smooth, we hope. Or it might go on forever if if the user is very bad at whisking or something. Anyway, assuming that the batter eventually gets smooth, we'll get to go on to the next step and fry a pancake in a pan. Imperative programs carry state, and in object orientation, that state is expressed in objects. The analogy here starts to get a little bit strained, but perhaps we might want to say something about, I don't know, what's the temperature of the batter, or indeed what's the smoothness of the batter at the moment. Now, what is object orientation? Now, here I have to perform something which is arguably a sleight of hand, because we're talking about object-oriented programming, and we're going to introduce it in a language, Java, which is not really a very pure object-oriented language. So, first of all, I'm going to tell you something about an idealistic view of object orientation, and then immediately afterwards I'm going to have to begin telling you about a respect in which Java is not an ideal object-oriented language. So hold your hats, okay? Now, what's object orientation really about? Well, all software engineering, all development and maintenance of complicated programs, fundamentally has to contend with the problem of change. If you simply have to write a program once and run it once and then you can throw it away, things are comparatively easy. The interest of software engineering and the difficulty of software engineering is that that's never what you want to do. Practically never. What you want to do is to have a program which will be able to be changed as the real world and the environment it has to fit into changes in a way which is reliable and economic. In other words, when something in the real world changes, you want it to be relatively easy to change the program to match. And the kinds of changes we're talking about could be changes in what your most important user wants the program to do, or it could be changes in some other piece of software that you have to interact with, or some other piece of hardware that you have to interact with, or whatever it is. But things change all the time, and software engineering is fundamentally the art of dealing with that change in an efficient way. Any program is going to have to provide some behaviour. That's what it's doing there, that's why you've got it. And in practice, that behaviour at some level involves some kind of data, some kind of state. So perhaps you're going to have to determine some data from the outside world, whether that's physical data about the world that you're interacting with, or whether it's data about what somebody wishes to do with the program, the changes that they wish to affect the world. And so that data is going to have to be managed inside your program somehow. And there are different ways of doing this. You've already seen one way of doing it in Haskell, most of you. In object orientation, the way we do it is we say that the program is organised in terms of objects. It's made up of a collection of objects. And each individual object itself has some data that it manages, it has some state, and also it has some behaviour. And so, in the ideal view of object orientation, running a program comprises setting yourself up with a collection of objects and having a starting object send a message to some other object to ask it to do some things. And it might change its state, it might send some messages to some other objects, they might change their state, they might do some things that affect the real world, and so it goes on. That's how your program actually runs, by members of a collection of objects exchanging messages between them and exhibiting behaviour as a result. Object-oriented programming languages today are almost all class-based, which is to say that instead of designing each object individually, we design classes of objects. We say in our program we're going to need, I don't know, we're going to need an arbitrary number of objects, each of which is going to represent an egg. And then perhaps each egg might be associated with some data, perhaps the weight of the egg. And each egg might be able to do a thing like, I don't know, break and release your yolk, or whatever it might be. And it's convenient as a matter of engineering to be able to describe the whole class of all eggs just once, to type one description of the class of all eggs into your program, and then instantiate it multiple times in order to describe multiple different eggs coming from the real world. So that's what we mean by a class of objects. The idea is very similar to the idea of a type of values that you've already met in Haskell. And indeed, for many purposes, you can think about classes and types as being the same thing. They serve the same purpose at the stage where we check whether we've written the program correctly, and we check things like, does it actually make sense to ask for this behaviour on this object, in our case of object orientation, or value in the case of a program in Haskell. Actually, classes in Java do a bit more than act as types, and we're just about to see that. But staying for the moment with a pure object-oriented paradigm, we can talk about what an object is by saying that an object has state, behaviour and identity. And this characterization, I think, is due to Grady Booch. Certainly I first met it in a book by Grady Booch. So when we say that an object has state, we just mean that there is some data associated with the object. We often talk about an object encapsulating some data, because the idea is that the object controls access to its own data. An object has behaviour, and what we mean by that is it is possible for an object to do some stuff. The stuff it can do, it will do in response to receiving messages from the outside. So if you want an object to do a thing, you send it a message and it will do some stuff. That's the idea of how it works. The idea of identity is slightly more subtle. What we're getting at here is the idea that two objects which have the same state can nevertheless be different objects. We might have two objects in our program, each of which represents an egg, And it might be that these two objects represent eggs of identical weight, but they might nevertheless not represent the same egg. They might not be the same object within our program. And we can tell that, for example, by invoking some behaviour on the object and observing that the effect of that behaviour might be to change the state of one object and not change the state of the other object. For example, if I have two egg objects in my program and I send one of them the break yourself message, then even though they started off having the same weight, if they're different objects and I send just one of them the break yourself message, that one ends up broken and the other one doesn't. Okay. This may sound completely obvious to you. You might say, why would I ever be confused about this? But once you start thinking deeply about the difference between the way things work in Haskell and the way things work in Java, you may end up confused. It is possible to end up confused. Good. Okay, so ideally, all the behaviour of your program is associated with objects, and the way your program does stuff is by objects sending one another messages, and each object doing a thing as a result of receiving a message. However, one of the ways in which Java is not a pure object-oriented language is that not absolutely everything is an object, and in particular in Java, unlike in Smalltalk, a class itself is not really an object. And whereas in Java all behaviour is associated with a class, it's not possible to describe a thing you want your Java program to do without putting that description inside some class. It is possible to write behaviour in Java which is inside a class but not associated with any particular object of that class. And in fact, you might even write a class in Java and never create an object of that class at all. And that's what we're going to see first, because that's how you write the very easiest, simplest Java programs. Now this is slightly unpleasant pedagogically, but bear with me. So here's a Hello World program. You may already have encountered the idea that when you meet a new programming language, one of the first things you should do is to write a program that prints Hello World and does nothing else. And so here is a Hello World program in Java. And we're going to examine it line by line in a moment. Hopefully you've already met the idea of comments, so you'll recognise that those top few lines there are comments. They are completely ignored by the computer, they're only there for the humans. That comment syntax there actually is relatively unusual in Java. It begins with /* and ends with /*, and everything in between those begin and end character combinations counts as comment. More usually we would comment line by line by putting two slashes at the beginning of a line that we wish to be ignored by the compiler, but you'll see that as we go on. Okay, so what does this do? It defines a class called Hello World. Within that class it defines a method called main, and the fact that this method is static tells us that it's one of those kinds of chunks of behaviour which is not associated with any particular object. That method takes some arguments. Actually, it ignores the arguments in this case, and then it prints out Hello World. That's what that system out println Hello World line does, but we're going to go through this in detail in a moment. So, when you create a new class, the first thing, as I already said, all Java code sits inside a class. You can't write any kind of behaviour in Java without putting it inside a class. Okay? People really often underrate the importance of the conventions that exist in programming languages about how you capitalize names, but actually it really is important. One of the reasons it's important is because when you want to talk about your program, you'll talk about it with other humans, and you won't say capital H hello capital W world. You'll say hello world, and you want somebody listening to you to know how to write that down out of their knowledge of the naming conventions of the programming language you're using. So please, even in the cases where the compiler will allow you to get away with not following the conventions, do follow the conventions when you write your own programs. So here's the first convention. Class names are capitalized and they're in what's called camel case. You can see that because the capitals that come in the middle of the words look a bit like the humps of a camel. That's how to think about that. Okay. Every class goes into a file of its own. There are some exceptions to that later, but we won't worry about those in this class. And the name of the file has to be the same as the name of the class, followed by .java. So we'll see in a moment, you'll use any text editor you like. gedit is one, my favourite happens to be Emacs. You'll create a file called helloworld.java, and in that file you will type the content of the previous slide to create your Hello World program. And so that's just an example of how you would set that up. If you sit at your terminal in your operating system and type the name of your editor and then the name of the program you wish to create. Of course, if you're in an operating system where you invoke your editor by double-clicking it, do that. So, let's focus on the outside first. It's often useful to focus on the outside of a program before you look at the inside. We have here public class hello world, open curly brace, close curly brace. Okay, that's the basic form of a class definition. It tells us the name of the class, which is hello world. It tells us that the class is going to be public. Don't worry about that for now. For now, all your classes will be public. And we're going to talk about the inside in a moment. By the way, I carefully said curly brace there because it said that on the slide. You'll certainly hear me say curly bracket by mistake later on. What do we have inside our Hello World class? Well, we just have a main method. In other words, we have a method whose name is main, and the main method in a Java program is special. The Java program always must have a main method. We'll see in the moment that the class you use to start your Java program is the one which will be expected to have a main method to actually get the program started. And then other code is invoked from inside main. So usually what will happen is that inside your main you will create some objects, and then having created the objects and set them up appropriately linked so that they know about one another, you will then send a message to one of your objects, and from then on things will go on more or less like the idealized version of the object-oriented program that I was talking about a moment ago. In this one, however, it's so simple that we haven't got any objects yet. Okay, but we've got a main method. It's public, and the main method always has to be public. It's going to be invoked from outside. It's static, as I said. It's not associated with any particular object. Void means that this method doesn't return a value. So methods might or might not return values depending on whether they're trying to change the state of objects or the real world, or else to compute something and return it. In this particular case, the point of this method is to change the state of the world, in this case by printing hello world out to the terminal somewhere. You might think of this as an effect if you're up on your Haskell terminology. The main method always has as argument an array of strings. So args there is the name of the argument, it's the name of the parameter that's being given to the main method, and that argument has the type array of string. That's string followed by square brackets, and we're going to talk about arrays more later on, don't worry. So there's a lot here that you're seeing for the first time, but we're going to go through it slowly. And again, just like the definition of the class being enclosed in curly braces, so also the definition of a method is enclosed in curly braces. And now finally we come to the very inside of the program, our single line system.out.println hello world. Now let's deconstruct that a bit. Now system.out is an object. It's a rather special one. It represents the standard out of your program, which in practice is going to mean, the terminal or wherever where you expect to see output from your program. Println hello world is a message. I already talked about messages being sent around from object to object. And the message is composed of the method name, which in this case is println, and again an argument. So in this case, hello world is an argument to the println method. So our object system.out is going to receive a message, and the message is going to be println hello world, and then it's the business of our object, it's the business of system.out to know what to do on receipt of that message. And in fact, what it's going to do is it's going to print out hello world on the terminal. Now the whole thing, the specification that we want to send a message to an object, is a statement. and statements in Java are terminated with semicolons, so that's why you have a semicolon at the end of the line there. What else is there to say? Yes, strings are demarcated by double quotes in Java. Not single quotes, not any other kind of quotes, but double quotes like that. And that's just the double quote character on your keyboard, not a pair of single quotes. A thing that's slightly inconvenient in Java is that you cannot break strings across a line in a file. We'll see various ways of dealing with the situation where that's inconvenient later on, but for now it's just a thing to know. So that's our program, but we can't run it immediately. We have to compile it before we can execute it. And compilation is the process of taking a Java source code file, like our helloworld.java, and checking that it's correct, and if it is correct, producing from it a Java bytecode file, a different file called helloworld.class. You can have a look at that too. The Java bytecode is the stuff that the Java virtual machine, which we'll talk about shortly, actually understands and can run. So the simplest way to compile your program is to use the javac, the Java compiler command, directly in a terminal. So you would type javac helloworld.java. And the compiler will read the source code of your program. If there are any errors in your program, you'll get an error message of some kind, which you'll then have to interpret. If there isn't a problem, then you'll end up with a Java bytecode file called helloworld.class, which you can then run. And you run it using the Java command. And again, the simplest way to do this is in a terminal. Now, here, one thing to notice is we are not going to go Java helloworld.java nor java.helloworld.class. We're just going to go Java hello world. And the way to think about this is that hello world is the name of the class that we wish to have interpreted by the Java virtual machine. When we get that right, what will happen is the program will run and it will print hello world, just as we want. So, in summary, we have an edit, compile, run cycle. So first of all, we type in the program using an editor and we save it to a file. And we are going to use the name of the class, of the main class, and the suffix .java. That's a source file. That's what we mean by a source file. Compilation is the process of taking a source file and turning it into a bytecode file, which in turn will have a .class suffix, the same prefix as the source code file that we started with. And then the Java interpreter in the Java virtual machine is going to read the bytecode file and execute the instructions in it. Now, we already mentioned the possibility that errors are found when you compile your program. That's a good thing, because if an error is found while you compile your program, then it doesn't trip you up later when you run your program. But sometimes errors might occur while the program is running. It might not have been possible for an error to have been detected at compilation time. And if that happens, the interpreter will stop. You might say it crashes, and you'll get an error message at that point. So, program needs to be compiled before it can be executed. Now, a very easy thing to trip up on is if you edit your program, you have to compile it again before you can run the new version. If you make the mistake of editing your program and then rerunning it and you forget to compile, you find that you're still running the old version. It still has the problem that you were trying to fix, and you can get yourself very puzzled and say, why? I just added that code, why is it not being executed? And the answer is because you forgot to compile it. So don't do that. We'll see later on how to use an integrated development environment. We might use Eclipse. In this course we're mostly going to use one called IntelliJ. There are many others. You might want to experiment with different things you can find. And one of the nice things that an integrated development environment might do for you is that it might automatically compile your code every time you change it, and that can be quite convenient. It might even do so in an incremental way, but I'd probably better not say any more about that right now. So, golden rules of programming. Compile often and save regularly. So, a classic mistake that students make is they try to write their entire program before they compile it at all. Ideally, you want to construct your program in such a way that you can get just a small part of it right, even if much of it is still missing, and then you can compile that bit and just check that that bit is working properly. And so you want to save and compile and run as frequently as you can manage. Try hard to split your work up into small steps so that you can do this often. Why? Because it is much easier to debug a problem that you might have introduced into your program if you discover that very soon after you made the mistake. Okay? If you've been thinking about 10 other things since you made some mistake with some line of your program, it can be much harder to go back and understand what it was that was wrong with that particular line. So, different points at which errors can be detected. The compiler checks syntactic correctness and quite a lot of other stuff as well. It checks the type correctness of your program, for example. Running your program will catch some other aspects of correctness, some semantic aspects of correctness. Of course, just running your program once doesn't prove anything about the complete correctness of your program, certainly not when you are writing programs that have to interact with the world, for example by taking data as input, and we'll talk later on about the importance of unit tests, which are ways of running your program with different inputs and in different circumstances in order to check a more thorough version of semantic correctness. So that sets the scene. Now let's go on and talk about some basic functionality within Java. One of the things you might expect to be able to do with a programming language is arithmetic, and here is a very simple arithmetic program in Java. We've got a main method just like we had previously, and again we're going to be printing some stuff. You can probably guess that what we're going to get from this one, we're going to say the sum of 6 and 2 is, and we jolly well would hope that the answer is 8, and indeed it is. And we're also going to try printing the quotient of 6 and 2 is, and printing again 6 over 2, and the answer there is 3. And you can see what's happening here is that somewhere in the process of compiling and running our program, that 6 plus 2 is being turned into 8, and the 6 over 2 is being turned into 3. Magic. Or as we might say, computation. Here's another example using strings. We can, in Java, not only add up numbers, we can even add up strings. This is called overloading. The way you add up strings, at least in Java and in many languages, is just to concatenate them. So in this case we are printing the concatenation of 3 strings. The name is Bond and James Bond. And by the way, this is already a very convenient way to handle the fact that you can't split strings over lines in Java, because what you can do is you can add up strings which live on different lines in your program. Notice that this whole thing is one statement. There's only one semicolon at the end, but the statement is allowed to be split over lines. There's no problem with that. Here's something that, coming from Haskell, you might find slightly more surprising. In this case we are adding up a string and an integer, and then another string. Adding strings and integers? What's really going on here is that the Java compiler is helpfully turning that 7, which looks like an integer, into the string that contains the single character 7, before doing string concatenation on it, which in this case is an example of DWIM, do what I mean. So, some basic definitions. A variable is a name that refers to a value, and an assignment statement associates a value with a given variable. And so this is the kind of structure we have. We may declare some variables. Here we're declaring 2 variables, a and b, and they're both said to have type int. That's the basic integer type within Java. The next line is an assignment. We go a equals 1, 2, 3, 4. So the whole statement is an assignment statement. A is a variable name. 1, 2, 3, 4 in this case is a literal. It's an integer literal. And the meaning of that statement is to say what we would like is that in future the value of variable a shall be 1, 2, 3, 4. Okay? Notice that the equals sign here is the operator in an imperative statement. It's not a logical assertion. Okay? That would be double equals, but we'll talk about that later. Okay? And similarly we can assign b equals 99. So you can think about this as saying that the declaration says there are going to be some boxes labelled A and B, and in box A I would like to put 1, 2, 3, 4, and in box B I would like to put 99. And we might put different things in those boxes later. It's possible to declare a variable but not assign to it, and that's usually a problem. It's an exercise for the keen to understand exactly what does happen to them in Java. It depends a bit on the circumstances. So often it's better, it's less error prone, to initialize a variable at the same time as you declare it. And that's what's going on in this example. That line int c equals a plus b, semicolon, simultaneously says c is going to be an integer variable, and the initial value of that integer variable c is going to be the current value of a plus the current value of b. Okay. Now notice this is really just the current value. If the value of a or b changes later, the value of c will not automatically change as a result of this line. But the point really here is that this is a combined declaration and assignment statement. Let's have now a slightly different version of the Hello World program. This one's going to have variables in it. In fact, this one is now going to have an object in it, which is slightly less special than system.out that you already saw before. Because what we're now going to say is that the variable name message is going to have type string, and the initial value of that variable is going to be the literal string hello world. Now here we are already starting to see the way that we kind of pun between classes and types in Java, because capital S string is not only a type name in Java, it's actually a class name. And so what we're saying here is that message is the name I'm going to use for an object of class string. And then we're going to use that object as the argument to the message println that we already talked about before. And so what's going on here is that we are sending a message to the object system.out. The message name is println, and the argument is another object. In this case it's the object that we now know as message. So Java has a bunch of built-in data types, characters, strings, integers, doubles and booleans. And if you say, hang on, one of those is not like the other, string has a capital S, well done, you're absolutely right. You will learn more about that shortly. Let's look briefly at what each of these types is and what you can do with them. So characters have literal values such as A and dollar and all the other things you might find on your keyboard. Notice that characters are surrounded by single quotes, and they're the single quotes that go that way. Okay, you may have to search around your keyboard a bit to make sure that you find the right one. In my keyboard it's somewhere in the bottom right underneath the @ sign. Your keyboard may vary. So the type char represents elements of the value set characters such as literal A or literal dollar, and things you can do with characters include compare them and get their ASCII values and all that kind of stuff. Okay. Strings we've already seen, they are sequences of characters, and examples are hello world and Java is fun, and you've already seen that you can concatenate strings using plus, and there are lots of other things you can do with them as well. The type int has the value set integers, and literal values of type int are exactly what you'd expect, things like 17 and 1, 2, 3, 4, and of course you can add and subtract and multiply and divide them, and just all the things you'd expect. Java's main floating point number is double, and you can notate that in scientific notation using E 6.022 E223, so that's 6.022 times 10 to the 23 represented as a double, or using decimal notation 3.1415. And again you can do all the things you'd expect to be able to do with floating point numbers on those Java doubles. Booleans represent truth values, and the literal values there are just true and false, and you can do ands, ors, nots, just the general Boolean logical operations that you would expect, and which I'm sure you're familiar with from Haskell. So here are some integer operations. we can get 5 plus 3, 5 minus 3, 5 times 3, no surprises there, except possibly you have to know that we use the star character for multiplying integers, not the x. 5 divided by 2 equals 2 might slightly surprise you. What's going on here is that the result of dividing one int by another int in Java is always an int. In other words, the fractional part gets discarded. If we want to know about what the remainder is, we can use the percent operator. So this amount, you can read this as the result, the fractional result of dividing 5 by 2 is 1. If I repeatedly subtract 2 from 5, what I end up with when I can't do it anymore without going below 0 is 1. Where the right-hand argument is an integer, you can think of this as asking what is 5 mod 2, if you're familiar with that from maths, but we'll see in a moment the right-hand argument doesn't actually have to be an integer. Dividing by 0 gives you a runtime error because you can't do that. Precedence works the way you would expect it to work from school arithmetic if you've ever met things like BODMAS or BIDMAS. The multiplication and division have higher priority than addition and subtraction. That can be confusing to remember. Things of equal precedence associate from the left, again as you would expect from school, but you can and should disambiguate using brackets any time you think the reader of your program might get confused if you don't. Default floating point type in Java is double, and here are some things that you can do with floating point operations. Let me stick that up there while I think what is there that I need to say about any of this. Using floatings point numbers, using doubles in Java is how we get what you might think of as a proper division that actually has a fractional part, as with 5.0 divided by 3.0. It's 1 point, many 6s and a 7. Okay, notice that we can have the percent between doubles as well as between integers as we saw them previously, and we use the same symbol. Again, it's overloaded. All of these symbols are overloaded for the different number types. There's a special double called infinity, so you can sort of do 1.0 divided by 0.0 and you won't get a runtime error if you're dealing with doubles. And then there are convenience functions like squirrut for square root. In this case, we're looking inside the math class for that convenient static method, squirrut, that will let us take the square root of a number. And the square root of -1 is not a number because we're talking about doubles here, not complexes. Okay. Now, you're probably already wondering, if you're thinking about the way in which dividing one integer by another and being required to get an integer might be inconvenient, that you might sometimes want to convert one type into another, because you might say, well, I really would like the kind of division that's going to be happy to give me a fractional answer, not just the kind that's going to be happy to only to give me an integer answer. And so this is where type conversion comes in. It can be quite handy. Conversion is sometimes done automatically, and so quite a lot of the time you won't even notice it, but if you think about it, you'll see that the compiler has converted one value into another value. So the first line here, the string 1234 plus 99, I'm already mentioned with the 007 example. What's going on there is that the Java compiler is automatically converting the integer there, in this case 99, into a string, and then applying the string version of plus, which gives you string concatenation, and returning you a string. So that kind of thing the compiler will often do automatically for you. A thing you'll very often want to do is to say, well, suppose that I want to go from a string to an integer, and the integer.parseInt method is how you do that. Again, parseInt is a static method within the integer class, and that is the syntax for invoking it. You can cast from a double to an int, and that's just going to give you a version of rounding. You should look up the details of precisely what that happens and or experiment with it. You can also use the math.round function. That will give us a long, which is a longer version of an integer. You can look that up. It's not going to be terribly important here. what else do we want to say? Yes, so you can get that and then you can cast that to an integer. In this case, 3 is not a particularly long integer, so that doesn't lose us any precision at all. That's absolutely fine. We can multiply things of type int by things of type double, exactly as you'd hope, because integers can be treated as doubles when we need to, and the compiler will arrange that for us. You don't have to give it special instructions about that. So those 2 lines with star probably aren't too surprising. What about 11 star bracket int close bracket 0.3? Well, what's going on there? What's happening there is that if we insist on taking a double 0.3 and casting it to an integer, that's going to discard the fractional part, and so we're going to end up with the integer 0. And then when we multiply 11 by the integer 0, we're going to get 0. On the other hand, on the bottom line here, if we do the multiplication first and then cast to an integer, we get a different result. Because if we just do 11 star 0.3, then as we saw further up, the result there, what happens there is that 11 is turned into a double, and the multiplication is done in double land, giving us the double 3.3, and then that double 3.3 is cast to an integer, meaning its fractional part is discarded, and therefore we get 3. Okay? So when you do arithmetic in Java, you have to think quite carefully about which things you want to be treated as having what types where, and make sure that you've got appropriate brackets and casts, if necessary, to achieve your intention. And I'll stop there.